This video will begin our discussion of section 13.2. We're going to start working on limits and multivariable functions. So to do this, like we've done for most topics, and we will throughout the rest of this course, is let's relate it back to Calc 1. So let's write the notation for a limit in Calc 1. This is the limit as x approaches a of some function f of x, and we'd say, hey, that's equal to L. And on the graph, we don't know if it's equal to L, but there was one thing we could do, and this is the way that usually most calc classes will introduce this idea of a limit, is that we're looking at what the graph is approaching. Let's say this is A, right? That is A. What we're concerned with, and hopefully you remember this, is that the limit only exists if we approach it from both sides, it goes to the same number. If we had some other function, let me just draw a picture up here. If I had something like this and something like this side would be approaching that big value up there. This would be on the lower value, meaning the limit would not exist. That's great here for 2 dimensions. Now imagine we have that path. There's no other way to travel on that green path. We only have 2 directions. Here's the problem with 3 dimensions. Think about some kind of plane, all right? Let's just think like maybe the side of a globe or something, one little part. Here's a plane or side or surface, some kind of surface, 3-dimensional surface. Well, I could approach this value coming from this way, right? I could approach this coming from this direction. I could come from this direction. And the natural question to ask from this, because in 2 dimensions, right, there was only 2 directions coming in, and that was every direction that would prove it. How many directions then are there when we're graphing in 3 dimensions? Take a look at that picture, and I just drew 6 paths, and they're all different. Can I draw more? Yeah, the answer is that there are infinite blue paths leading to that red dot. So in one variable, this is a curve, it's a certain path, so it limits us to 2 directions. That's what my notes say. 2 variables, we have a surface, right? Some kind of surface. There are an infinite amount of paths along the surface that approaches at one point. To prove, and back from Calc 1, we would prove a limit exists by showing that both sides, the right side limit and the left side limit, went to the same value. We would have to still apply that here to 3 dimensions and prove that all paths go to that same point. That can be extremely difficult or even impossible at times, right? There are ways around it. I'm going to show you a few different things later based on continuity and the squeeze theorem to show that a limit exists. For the most part here in Calc 3, your problems are going to be showing that a limit does not exist. Think about this. If I had, I always compare this, we have a bunch of people in the room, right? 50 people in the room, and I make this statement. I say, everybody in that room has a black shirt on. Well, you would go and you'd find, hey, there's this one person who has a green shirt on. You were wrong. And you only had to show me that one person with the green shirt to prove that my statement that everybody had a black shirt on was wrong. So when we want to prove something isn't true, we only have to find one case. If we want to prove that it's true, we have to prove all cases. If we want to prove that it's not true, that means we would only have to prove one, because that proves not all. Okay, so what we're going to do is we're going to create paths in 3 dimensions, and we're going to find 2 paths that go to a different value. And when we say value, we mean the z value, right? The up and down value. We want to find 2 paths that go to 2 different values. Then we have proven that it doesn't exist. Let's take a look at our first example. These are pretty difficult, so I'm going to do quite a bit of examples in this video. So this may be on the longer side, but it's better than the alternative route. Trust me, these are pretty difficult. So we want to show that doesn't exist. The first thing we do with limits every single time, just like any other limit, is we plug the values in. I plug x and y in. I get 0 over 0. And maybe some of you guys are like, well, if I get 0 over 0, can I use L'Hopital's? Well, then what do I take the derivative of? Do I take the derivative of y, x? If I do implicit differentiation, then I'm also introducing dy dx's. This is going to lead us to something later, and some of you guys have already been working this probably in some of your engineering classes. But we'll deal with some levels of partial derivatives, that's what it's called, later. actually here in a few sections. So when we plug in 0, 0, doesn't work. So we need to find some other path. So when our point is 0, 0, we always pick the first two paths that we're going to try is going to be when x is 0 or y is 0. Right? That's based on here. If that was a different point, if that was like the point AB, we would do x equals a and b equals a. But in this case, we got that 0, 0. So we're always going to pick x equals 0 and y 0. So let's talk about that path. First, we need to understand, what does that even mean? X equals 0 path. So what that means is this is some kind of function. It's a surface, right? There's two variables. That means 3D graph. It's a surface. Right? Since it's a surface, that means we have to come up with points approaching the point 0, 0. Well, if you think about 3 dimensions, let me pull my graph out of these photos. I think this one's good enough for this. All right, we're going to this point, and we're traveling. The surface is like a blanket on that, right? And this point exists on that blanket, or surface, or mountain, or hillside, however you want to think about that surface. And what we're going to do is along x equals 0, well, x equals 0 is this plane, right? It's that plane right there in the middle with x being 0. The other way, sorry, this way. So it's with x being 0, we would have the flat plane, the zy plane. So this is the zy or yz plane, however you want to say it. Probably the other way around is the appropriate way, but it didn't really matter. YZ plane. If x is 0, we're in the YZ plane. So now we have some kind of function. Here's the point I'm trying to get to, and we're stuck in the YZ plane. So all we're going to look now is we have some kind of path, and we're going to look and see what happens on the surface as I go along the surface, but I stay in that plane. So that is my path. It's going to be a straight path. Remember, this is a surface, so I have an infinite number of paths coming any direction. It's not like a space curve where there's only one line going to that point. It's a blanket. It's a hillside. That point is just a flag in the ground, or something on the blanket to tell us to go to that point, right? But when we do x equals 0, that is staying in the YZ plane. Right? In the YZ plane, I don't go to the towards that positive x's. I don't go negative x's. I stay in the plane. Okay, so I hope you understand what we're talking about when we say along x equals 0. Right? Let's write a note for ourselves in case you're looking at this later and you're wondering, I don't remember what we were talking about. I think traveling has one L. I'm not sure. We'll just write it. Traveling along the surface. So remember, the surface is like a blanket, hillside, right? It's not a curve. Directly over or under, we don't know where we are, the y-axis. Think of that picture. Would be under the y-axis or over it. All right, so let's think about what that limit would look like. Then we'd have the limit. I need to start writing a bit smaller. The limit as, all right, we're going to be approaching 0, 0 still. But now we're going to let x equal 0. So we have that over 0 squared minus y squared over 2 times 0 squared plus y squared. I can rewrite this limit now. I don't need to pay attention to the x. So I'm just going to do as y goes to 0. And then what we have here is we have negative y squared over y squared. So that is a limit as y goes to 0. I'm just going to go all the way down to my constant. And then remember back from Calc 1 at the very beginning, the limit of a constant is the constant. So that's the path along x equals 0. All right, I'm going to make this smaller to make more room for myself so I don't have to do a whole nother page because we only have to do one more side. We'll do this. Shrink it in. All right, so now we're going to do along y equals 0, the other path. We always try these two first. So I'm going to write out what this means. Traveling, this would now, if we let y equal 0, would be stuck in the xz plane. along the surface directly over under x-axis. Sorry, I'm at the edge of my iPad, so it's harder. There we go. The x-axis. All right, so we do that same type of limit. We have x is still there, but y is 0 now, going to 0, 0. So I get x squared minus 0 squared over 2x squared plus 0 squared. We get the limit as x approaches 0. Please write limits every time. Please don't make me count off. I hate counting off, but I will. You guys are in Calc 3. It's time to write things formally. Do not drop the limit until you get done taking the limit. All right, I got x squared over 2x squared. All right, that's the limit. Still write it. I didn't take it. X equals 0 of 1 over 2. The limit of a constant is a constant. So since, right, we need a statement for this type. If you just write this down and write nothing else, you're going to miss some points. Since, and I'm going to have you write like the bare minimum. Since negative 1 doesn't equal 1/2, the limit d and e does not exist at 0, 0. We want to say where at. You don't want to just say does not exist, because the limit would exist maybe at another point. Okay, so that's how we do our limits. We didn't prove that the limit existed, right? We proved that it didn't exist by finding two paths that were not equal. If we wanted to prove that it did exist, we'd have to prove that all paths go to the same path. Highly unlikely possible to do that, but there are ways around it, and we'll get to that. Let's make a few notes here for yourself on how to try these. I wrote just a general limit up there. If we're going to 0, 0, we always try x equals 0 and y equals 0 first. If the point's different, like if this is an a, b, and I mentioned this above, then it would be x equals a and b equals, or y equals b first. Most of your problems are probably going to be 0, 0, but we'd want to try that first to see what happens with that. If those do not work, we have to choose other paths. Sorry for the typo there. Be certain one, have to make sure, because if it doesn't make sense if it's not the case, that the point that you're trying to take the limit to is actually on your path that you're choosing. What does that mean? When we chose earlier, we had our like axes, and I showed you guys like, okay, well, we have some graph coming here and going to, it was 0, 0, so we probably should make it go there. 0, 0, the path actually has to go through there. If you pick some other path that doesn't go through the point that you're trying to take a limit, it's not going to make sense. It just is nonsense from there. If you have to choose another path, this is the key to figuring it out. Try to substitute so degrees of numerator and denominator are equal. We're going to do an example right here of what that means. What you're going to always want to use, even if choosing x equals 0, y equals 0, if that doesn't show that they're not equal, like we get the same number on that, you're still going to choose one of these as one path to help with that. Then you don't have to go find two new paths. You need to go find one new path that doesn't equal the x equals 0 or y equals 0 path. All right. Let's give this a try on this example. So the first thing we're going to do is evaluate one, can you plug it in? Well, if you plug 0, 0, you get 0 over 0. L'Hopital doesn't make sense at this point. So we are going to try the paths that make the most sense. We are going through 0, 0, so we're going to try x equals 0. All right, so that's the limit. I know x is going away, so I'm just going to write y equals 0. That's what it's going to. And then I'm going to plug in 3 times 0 times y over 3 times 0 squared plus y squared. This equals the limit as y approaches 0 of 0 over y squared. Well, the way I think about this, there's a couple ways to think about that. What I do is I just evaluate my limit all the way down before I take it. So that's a 0. And then I think Calc 1, the limit of anything going to 0 is 0. If I tried to evaluate it here, I can't, right? I get 0 over 0. But if I have simplified the inside as far as I can, then I just have the limit of a constant. I hope that makes sense. Like jumping from here to here, without thinking about that middle step. I guess if you're thinking that middle step, then it's true, and I would count that. But if you tried to just like plug it in here, actually you wouldn't get 0 anyway. But if you write that, I'll count it. But if you plug 0 into y, you'd get 0 over 0, which means you would say it doesn't exist. I can't take that limit, but we actually can. Based on the limit of a constant is a constant. All right, so I tried the other path along y equals 0. Remember, we have infinite paths, and we're trying to find 2 of them that don't go to the same place. So making y 0 would mean we're focused on x. All right, I got 3x 0 times 3x squared plus 0. We get the limit, I didn't evaluate it yet, x approaches 0, of 0 over 3x squared. I would not plug 0 into x. I would simplify, the argument, what we're taking the limit of. That's a 0, which tells me the limit is 0. Okay, this proves nothing. It just proves those paths go through 0. Doesn't prove it exists, doesn't prove it doesn't exist. So we need to pick another path. Pick another, if I could spell another right. Is that right? No, sorry about that. Another path, wow. Pick another path, y equals some function of x or some x that is a function of y. So something that relates it to the other. And this is where that the statement on that last page came in of to try to, I think it's actually at the top of this one, it's on the back of my notes, this line. Try to substitute so degrees of numerator and denominator are equal. So if I'm like looking at my denominator, okay, the y there has a y squared. If I could make x squared y squared, then the degree of the bottom would be a y squared when I add those together. Think about that. X I replace with y, then I can add the denominator together. That would put a square on the bottom. If I put a y for the x on top, that would give me a y squared, meaning y squared over y squared. That's what I want to do. So I am going to make my y or my x, either way, I'd write it the same way, along this path when y equals x. So that means, right, I replace everything that was a y with x. So I get 3xx, 3x squared plus x squared, right? That's the limit. Oh, and then we're dealing with x's, so I keep my x, and it goes to whatever point it was originally going to. It was going to 0, so I keep the 0. The reason I knew it was an x is because that's what I have left. Putting a y would do nothing. I get 3x squared on top. I get 4x squared on bottom. What this does is it creates that constant. The limit as x approaches 0, we get 3 over 4, which is 3 over 4, which is not 0. So we can write out our finishing line. Some teachers are going to make you write more here, maybe in your physics classes. I would feel like as you go through your engineering classes, they're going to make your stuff look more and more like reports and stuff like that. But I am like cool with the bare minimum here. Since 0 does not equal 3/4, the limit d and e at 0, 0. That is the bare minimum. If you write less than that, I will count off. Some form of that. If you want to write it out, like on my notes, I say, since the two paths lead to 2 different points, 3/4 do not equal 0, then the limit does not exist. That's what I did. This is the bare minimum. I don't want less than that. So please write at least that much. All right, I have quite a bit of examples on this. So this video will be on the longer side. Let's try another. All right, we always try the same paths first. Along x equals 0. We'll try that. All right, so that's the limit as y approaches. And the reason I knew it was a 0, you should validate that, right? That this is 0, 0. Okay, the limit as y approaches 0, and I'm going to put a 0 everywhere there is an x. Right, on top, doesn't matter what any of that is because the 0 times up front gets me a 0 on top, and then a y to the 6th. And then this comes down to, if I plug 0 in right now, I get undefined. But if I rewrite it as y approaches 0 and just simplify that to a 0, then I can use basic calculus of a constant being a constant for a limit. So I know from that side, gives me 0. We're going to try long y equals 0. So we keep our x, right? And we put a y, 0 for y. So I got x times 0 cubed cosine 0, x, right? Because we plug for y. Then we got 2x squared plus 0 to the 6th, right? I rewrite that. You can tell what's going to happen here. We get a 0 on top. We get a 2x squared on the bottom, right? I can simplify that, not plug it in. So I keep my limit, and that's equal to 0. We have nothing, right? We proved nothing. We just proved that those two paths have the same result. Doesn't prove the limit, doesn't disprove the limit. All right, now I'm going to use that same trick. I want the denominator and numerator to have the same. So what I typically look for is I look for the largest. So y to the 6th. I'm thinking about what can I make x, what form of y, that way x squared is y to the 6th. Well, that would be, okay, x to the 3rd, right? Because if I times it, if I squared, I would just 3 times 2 to get 6, or x to the 3rd times x to the 3rd gives me x to the 6th, right? Or y, I guess, rather, not x. There we go. Now that makes sense. Think about squaring the left side, I get x squared. Squaring the right side, I get y to the 6th. If I make that substitution, I have y to the 6th on the bottom. All I have to do is make sure I got y to the 6th on top. Well, if I put it right here for that x, y to the 3rd times y to the 3rd is y to the 6th. So that's the path I want to use. So along x equals y to the 3rd. All that was based on was matching my exponents. So I have the limit as, okay, and I'm going to replace first because that'll make it more obvious of what goes under that limit. I got, okay, we're going to get y to the 6th, cosine y to the 6th, y to the 3rd, I think. Yeah, y to the 3rd. Okay, and then we get, on the bottom, we have 2y to the 6th plus y to the 6th. All right, we rewrite our limit. And this tells me what variable it's y, and it approaches the same number it was approaching in the original problem. Y goes to 0. All right. Up here, okay, notice we're going to have y to the 6th. I'll show every step for this. Cosine y to the 3rd. Over 3y to the 6th. Now I can factor out that y to the 6th, or cancel it out, I mean. Guess we are factoring and calling it a 1. And we get 1/3 cosine y to the 3rd. We can now take this limit. Cosine of 0 is 1, meaning this is 1/3. Right, here's the bare minimum that you can write. Since 0 does not equal 1/3, the limit dne, I always have trouble with that n, I don't know why, at 0, 0. All right, so again, just disproving. All right, let's get some more examples. I hope this is feeling okay. I know this is more examples that I've done in the past for my classes, and I feel like it is feeling better to me, at least going through it. So I'm hoping that you guys are feeling the same thing. All right, so let's try another one. All right, so it looks messy. The first thing we'd want to try is to plug in 1 and 0 into everything. You can find out really quickly, okay, well, we get, what do we get on the bottom? We get 1 squared plus 0 squared minus 2 plus 1. All right, that gets us a 0. So we can't just plug it in. We always want to make sure, if we can just plug it in, we plug it in and stop. I've had so many students for the plug it in problems try out to do all this different calculus, and they didn't have to. They just had to plug it in. All right, so along y equals 0, let's do that first. That's our first. The reason we went with that is because of this, right? The y is 0. So the limit as I keep my x and I approach the same number it was approaching, 1. And I replace 0 for all my y's. X squared plus 0 squared minus 2x plus 1. That gets me a 0 over x. Oh, see, and I dropped my limit. Make sure you do it, but I caught myself. X goes to 1 of 0 over x squared minus 2x plus 1. That doesn't matter. We get 0. Right? We don't even we don't want to think about plugging it in there, because if we think about plugging it in, and another way to think about this is at this point we can use L'Hopital's, right? I can use L'Hopital's there. Okay, that's one path. Let's try the other path. Now you may be tempted to put x equals 0, but x is not going to 0. X is going to 1. As I kind of mentioned in passing each time we talked about it. So we have the limit as y is approaching 0, the original number it was approaching. And now I'm going to put a 1 everywhere there was an x. 2 times 1 minus 2y. 1 squared plus y squared minus 2 plus 1. Right, this is equal to, I'm keeping my limit. We're writing it every time we take it. Usually we don't even take it till the end. So 2y minus 2y, we get a 0 up top. On the bottom, we get a y squared. That is also equal to 0. You can use L'Hopital's if you wanted to try to plug it in, or you could 0 over that number would be a constant. All right, so it doesn't work, unfortunately. Now, I'm going to rewrite this problem for a moment. We're going to try to manipulate the beginning problem. I'll write down the limits so we stay disciplined on that. And what I'm going to do is rewrite parts of this equation. Notice there's a 2y in both terms, so I'm going to put an x minus 1. If I put a y squared first, then I have, let's write off to the side here, I have x squared minus 2x plus 1. You may or may not see this. This is x minus 1 squared, right? It's factorable. Think about multiplying that out. We don't just square x and square negative 1. We FOIL if you want to use that or distribute. So this becomes down here plus x minus 1 squared. After I do that, the path to choose to go down becomes obvious. I want to go along y equals x minus 1. What's going to happen is I get to make all those replacements, right? The limit, okay, I use that y is going to that. So I'm going to replace first before I write down, okay, I got 2y, x minus 1 becomes y. And then I got y squared plus y squared. So the remaining variable is y, and y was going to 0. I waited till I put that y to make it more obvious for myself. The y is the limit as y goes to 0. We get 2y squared over 2y squared. That's a 1. So the limit is equal to 1. Now here's the bare minimum you can write. We have found two limits that go to two different places. So since 0 does not equal 1, the limit does not exist at 1, 0. I'm going to keep saying this. That is your bare minimum that you can write after a problem like this. If you don't write that, you're going to miss points. Please don't make me count off for stuff like that. It feels silly, and I cringe through counting it off. So please, yes. All right, let's take a look at, we have a few more, and then I'll break these videos up a little more. So I have two more examples. Let's show that this limit doesn't exist. Notice the change here. The change was that we went from an xy to 0, 0 to xy and z going to the ordered triple 0, 0, 0. Right, for three variables, the way to think about it is a parametric equation. So let's write that down for a note. For three variables, paths are now parametric. And then we'll put in quotes here, t, because that's what we use for parametric. And then also always, for these problems, always choose an axis as first path. And then we'll come up with the second one after we do that. So let's do that first. We'll do along the x-axis. So along the x-axis, what that means is y is 0 and z is 0. All right, so we get the limit. If those are 0, we're left with just x. You could wait if you wanted to and make your substitutions and see what's left. We get x times 0 plus 0 times 0 plus x times 0. On the bottom, we get 0 squared, or we get x squared. That wasn't 0. Plus 0 squared plus 0 squared, which gives us the limit as x approaches 0 of 0 over x squared. We can use L'Hopital's, or we could simplify to get a 0. All right, so that's along x-axis. We always want to use one axis first, and you just let the other two variables be 0. Think about why that's true. Understand why that's true. All right, we're going to call this one, we're just going to say along, and we're going to call this path C. All right, what path it's going to be is we are going to create a parametric equation to help us out. Now, what I'm looking at is the degree thing again. I'm going to let x equal some form of t, y equal some form of t, and z equal some form of t, and I would really like to match the degrees. Well, an easy substitution I always try first is what if I just let them all be t, especially with some kind of thing up here. Well, I would get t squared plus t squared plus t squared, right? So I'd get some form of t squared. Up here, I'd get t squared, t squared, t squared, right? Oh, this would just be 3t squared for that, right? T squared plus t squared plus t squared is 3t squared. We'd get the same thing on the bottom. You can see the t squareds are going to cancel. Now we just got to show it. So that was inappropriate. I always start there. So now I make my substitution. I'm going to leave the limit there first. And we're going to fill everything in. So I get t times t plus t times t plus t times t. Then I get t squared plus t squared plus t squared. Right? You can see we're going to get 3t squared on top and on bottom. So we're going to get the limit of 1 now. We got to talk about what does t go to, because we know it's t, that's all we have. But what does it go to? Well, as x goes to 0, as y goes to 0, as z goes to 0, so does t, right? If t goes to 0, those also go to 0. That's what we want. We want it to match that same point. Well, the limit of t 0 is 1. Well, that's just basic calc. We get 1. Now we have two different paths. So we write the bare minimum here. Since 0 does not equal 1, the limit d and e at 0, 0, 0. So again, even if there are three variables, we're looking for another path. This parametric equation stuff is the key to this. All right, let's do one more example of proving a limit does not exist. We, again, have three variables going. We have ordered triple, right? The expression has x, y's, and z's. I always choose axis first, so along x-axis, whatever you want to choose. You could consider what would happen if you let the others be 0. In this case, it really doesn't matter. It's pretty symmetric. So we have x still. X is approaching 0. And this means if you want to write y equals 0 and z equals 0, that's what that means. So we get x times 0 squared plus 2 times 0 squared plus x squared, or over x squared plus 2 times 0 squared plus 0 to the 4th. That gets me the limit, write it again, x approaches 0 of 0 over x squared. L'Hopital's, or I can simplify, tells me this is going to be equal to 0. All right, so I'm trying to find some other path that does not go to 0. I call it just C. And we're going to do x equals, y equals, and z equals. I always start here with just a t on all this. If I plug all that in, My powers on the bottom, check it out, I get t squared plus 2t squared plus t to the fourth. I really wanted those to all to combine to 1 in hope that the t's will cancel. So it would make sense if I'm going to match the highest one. It's hard to pull them down. I don't want to do that because then I'd have to start doing 1/2 and 1/3 as powers. We don't want that. So what we'd rather do is just get maybe these two to match the fourth. That means that this would have to be a 2 and that would have to be a 2. Because when I square them, I get t to the fourth then. Right? I hope you can see how I did that. All I did is I started with t's and then I tried to match the highest one. They don't always have to be like a uniform change, meaning I'd change this to t squared and change that one to t squared. I could have just tried x, but it makes sense that both of them had to change since they were both t squared up here, and I need a t to the fourth. Okay, so the limit, now consider t, as t goes, we're trying to get to 0, 0, 0. That means as t goes to 0, those are going to 0 as well. Okay, now I replace. I get t squared times t squared plus 2 times t squared squared over t to the fourth plus 2t to the fourth plus t to the fourth, because z was t. Right? This is equal to the limit of t approaches 0 of, okay, up top we get 1t to the fourth plus 2t to the fourth, we get 3t to the fourth. And on the bottom, we get 3 to the fourth, overall, you guys can see it, 4t to the fourth. That is equal to the limit as t approaches 0. That is a nice, pretty 3/4. I can use L'Hopital's if you wanted to. Eventually, you'd get down to the ratio of 3/4, or you can just simplify it down to 3/4 and know that the limit of a constant is the constant. All right, so those are two different paths, 0 and 3/4. So I write, since 0 does not equal 3/4, the limit dne at 0, 0, 0. Okay, as you can tell, these aren't easy. They're not just follow these 4 steps and it works out the same time. You have to actually think about those different paths that are happening. Get some practice under your feet. This isn't one that you watch me do 3 or 4 and then try to risk it for the test. This is you do your homework, you do maybe the odd problems in the book as well, like the ones I don't assign, odds and evens, whichever ones I don't give you guys a list. There's 1 or 2 out of each section. But jump in those sections and find other ones and practice doing this. If it's too difficult, you have the solution manual. You can take a look at that and get unstuck that way. Practice, 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 practice. This is, I think, out of this, and it's it's subjective, not objective. I think this topic here, the limits of multivariable, is harder than the stuff that we're going to be doing later. Totally subjective. You may think differently. I've had students say differently as well, but yeah, practice.